Okay, hello everyone. Today I have the pleasure of introducing to you Fedor Fomin, who's going to talk today. I'm sure many of you know him from his work on, well, many things, but I particularly know his work on bidimensionality and representative families and other things. He is a co-author of 3 books on exact and parameterized algorithms. And that's why also he is the perfect guy for today's talk, which is going to be a survey talk on parameterized complexity with the title Paths, Cycles, and Beyond. And Fedor will talk about all the new parameterized algorithms for finding long paths and cycles in graphs. And in future, we hope to have more of these kinds of survey talks. And if you want to stay informed about our Colloquium, we have a Twitter feed, a Facebook page, and also now we have a mailing list you can assign for. Maybe I will send some information in the chat in a minute. If you have any questions during the talk, on the right-hand side, you will find the questions button. You can write your questions in there, and then maybe the easiest is if at the very end of the talk, Fedor can answer all of the questions. Also, I hope many of you will stick around after the talk for for the networking session. And with that, Fedor, please, you have the floor.
Yeah. Thank you very much, Andreas, and thank you very much. Thank you all the organizers. I think it's a really great idea to have this colloquium. And yes, so in this talk, I will survey results about parameterized algorithms about finding a long path or a long cycle in a graph. So I will give some historical overview, and then I will move to the topics which are closer to the things which I was doing. So the 2 main heroes of the talk are the longest path and longest cycle. So in the longest path problem, we have a graph G. This graph can be undirected or directed. We have an integer parameter k, and we want to decide whether G contains a path of length at least k. And very similar the problem for longest cycle. We have a graph and integer k, and we want to find out whether graph G contains a cycle of length at least k. And of course, when we speak about longest path and longest cycles, I couldn't resist of not mentioning the historical parts. And definitely this problem is a generalization of the Hamiltonian cycle and Hamiltonian path in a graph. So the topic which was attributed to Sir William Rowan Hamilton in the 19th century. But apparently this problem was much older, and there are reference to the Indian poet and scientist and mathematician Rudrata, and also to the Middle East Al-Aldi Ar-Rumi. And yeah, so this is definitely a classical problem, and perhaps this is the oldest problem in graph theory. And if you look at people who are working on Hamiltonian cycles, on longest path and longest cycles in a graph, this is really a hall of fame of graph theory. So actually, I put several photographs and several names here, and after some time, I just ran out of space and I ran out of patience. Because basically, you just take any big name in graph theory from 1960s or 70s, and there is a theorem called by this person about paths or cycles in a graph. So it's like that's extremely well-studied area. And in algorithms, of course, people were paying attention to longest path and longest cycles and Hamiltonicity for a long time. So it's special in mathematical programming and operation research. It's a special case of the travel salesman person. And there is also algorithm, one of the first actually the dynamic programming algorithms is CARP and also Bellman algorithm, which solves travel salesman problem. And also, of course, Hamiltonian cycle in time 2 to the n, where n is the number of cities or a number of vertices in the graph. Also, the problem is one of the first problems. It was in the list of CARP of NP-complete problems. So the problem is, of course, NP-complete. And in parameterized algorithms, again, so the problem was studied even before parameterized complexity was invented. So there was a pioneering work of Burkhard Manin, which was unnoticed for a long time, which developed algorithm of running time k to the k times some polynomial of the input length of the algorithm which finds a path of length at least k. And actually the idea, this is what we will call now this type of method or technique. The idea was they're using representative sets. Also, quite in the same time, Hans Badlander developed algorithm, and this algorithm was using trivial arguments. And again, this algorithm was of running time k to the k. And the problem became really popular after, in quite influential work, Papadimitriou and Yanakakis asked the question whether there is an algorithm which finds a path of length log n in polynomial time somewhere. And this question was answered almost the same year. Yes, so okay, so here is just because 1996 and 1995, because as usual we have a delay between conferences and journals. So this is a journal of ACM paper of Noga Alon, Raphael Juster, and Uri Zwick, who resolved this question by giving what we call in modern language single exponential parameterized algorithm. So the algorithm which works in time 2 to the big O of k and times n. And this is the paper which introduces quite fundamental technique called color coding. And this technique is used a lot. And this was extremely, and this is an extremely influential paper. And after this paper appeared, there were a lot of different and interesting techniques developing for k-path, for k-cycle, for longest path, for longest cycle, for Hamiltonicity, and around. And you can ask, why do we need so many different algorithms for solving this problem? Well, my answer would be very simple. Look, it's a very beautiful and very fundamental problem. And very often when we design an algorithm for this problem, this type of techniques or methods, they work for in much more general settings, and sometimes it's quite unexpected applications. And the other thing why people care so much about this type of new, or why we need new methods here, is just there are different important variants of longest path and longest cycle. Because, for example, there is a breakthrough algorithm of Björklund for Hamiltonicity, which was also then extended by Björklund, Hustvedt, Kaski, and Kovista for k-path. So this algorithm solves k-path faster than 2 to the k. And 2 to the k, for a long time, it was believed like a natural bound. But this algorithm is randomized. And for example, we still don't know any deterministic algorithm solving longest path faster than 2 to the k. So there's a difference, randomized deterministic algorithm. Then there's also a question, so what happening, because again, so Björklund algorithm, it doesn't work on directed graphs. So what happening if the graph is directed, and here the story is different? What happening for the cycle and for the path? Again, so it's slightly different running time, slightly different algorithms. Then the problem can be weighted. People can also care about the polynomial space algorithm. And this is why, but also it's a nice area, because it seems like the problem can be approached from different sides of computer science and mathematics, and this is always exciting and interesting. So far in parameterized complexity, there are several mainstream directions on Hamiltonian or on longest paths and cycles. So one direction is to obtain better algorithm, people improving the running time of the algorithms, but also develop for more general problems in, again, like polynomial space algorithms, deterministic algorithms, algorithms which solve weighted problems. So the other also very popular direction of research, and research which is very close to my heart, is the development of sub-exponential algorithms on geometric graphs, so like on planar graphs and on unit disk graphs, and the graphs which are intersections of different geometric objects. This is also a very nice and beautiful area of research, but I will not speak at all about this area in this talk. But again, this deserves another survey. And what I will talk today is the family of results where we are looking of longest path beyond. And beyond here, it's ambiguous. What is beyond? One thing beyond could be that beyond is some combinatorial bound. And the other thing which is also beyond is usually for this type of problems, beyond means that for this type of problems, we cannot use color coding and other already standard techniques in the area. So definitely this type of techniques or this type of solution of these problems, it goes beyond the known methods. So, and I will, in this talk, I will speak mostly about this type of beyond type of problems. And here there are a lot of also interesting open questions, and every time I will be speaking about some new problem, I will be speaking about open questions. So there is a lot of, in my opinion, there is a lot of nice problems for research left here. But in order to understand what I mean by beyond or beyond color coding, it's nice to know what color coding does, right? So just a reminder. So what color coding does, I will explain it very fast. But the crucial thing why color coding works for longest path is the following very trivial observation. The following two statements are equivalent, right? In a graph, if I have a graph and I want to decide whether a graph contains a path of length at least k, or if I have a graph and I want to check if a graph contains a path of length exactly k. Right? These are the same things, because if my graph contains a path of length k, then it also contains a path of length at least k, right? And also if my path contains a very long path, then I just take any part of this path and of length k, and that will be exactly k. And this is a simple observation, but it's very crucial for color coding to work in its pure form, because what color coding is doing, we just color vertices of the graph uniformly in random in k colors. Yes. Then what will be the probability that a path on k vertices has all its vertices colored in different colors? Well, any set of k vertices colored in different k colors, right? Well, so this is the probability. The total number of all coloring of k vertices with k colors is k power k, right? And the number of good colorings is k factorial. So then it's this probability is k factorial over k power k, and by using Stirling approximation, it's a standard thing. We can bound this as a 1 over e power k. And then, so as far as we colored the graph, and if we assume that this coloring has this nice property that our path is colored, then it provides a lot of information. And so, for example, if you care about k to the k algorithm only, so what you can do, you just guess the number or the ordering of the colors, and then it just you're looking for a path going from, or you just go breadth first search from the first color to the last color. Or also, if you care about single exponential algorithm, you can do it in 2 to the k. times n by doing dynamic programming, and this dynamic programming is very similar to dynamic programming of health and carb for a traveling salesman person. So the only thing that you go not over subsets of vertices, but you go over all subsets of colors, and every time at every step of dynamic programming you care that you have a realization in of a path with this set of colors. So this is definitely doable. And then but the probability is quite bad, but then of this event that your graph is properly, that our path is properly colored. But then there's a standard trick. So if the probability is bad, you just do more experiment, and if you want to have a constant probability of error, then you do it e power k times. So you do e power k experiments, and for each of the experiments you spend 2 to the power k time to do dynamic programming. So in total your running time would be 2e power k. So this is the algorithm. This is a randomized algorithm. So if it says yes, you definitely have a solution, and if it says no, then with a constant probability, the algorithm makes a mistake. And there's also quite standard tools. I will not be speaking about them at all, but there are standard tools how to de-randomize this type. So color coding. Yes. And again, so the crucial property here. So why color coding work? Was that we were looking for a path on exactly k vertices, because when we have a path on k vertices, we are able to estimate the probability that this path is properly colored, and after that we are able to do the job. So for example, even for the problem of finding a longer cycle, these arguments, they do not work directly. So how come? It's just because the following two statements are not equivalent, right? It's not the same thing that graph contains a cycle of length at least k, and graph contains a cycle of length exactly k. So for example, take a cycle on n vertices, right? And take k equal to, for example, 3, right? So this graph has a cycle of length at least 3, but it doesn't have a cycle of length 3. So, and this means that I just cannot use the same arguments as for color coding for longest cycle. Of course, there are, for undirected graphs, there is a simple trick which reduces the problem to solving longest path on undirected graphs. It's a simple H contraction trick. So the argument is the following. So I'm just, first of all, I guess if the longest cycle in the graph is if its length is between k and twice k. If its length is between k and twice k, I just can guess this length and do color coding for this number and find this cycle. And if the length is more than 2k, then what happens? What happens if I just contract any h in the graph, right? So if this h is outside of the cycle, I don't change anything. So the new graph also contains a long cycle. And if this h is in the cycle, right? So the only thing I can do, I cannot decrease the length of the cycle by more than twice, right? So anyhow, when I contract any h in this graph, I will have a cycle. If I assume that my graph contains a cycle of length twice k, then by contracting any h in this graph, I will still have a graph which contains a cycle of length at least k. So then my algorithm will be, I'm just checking if my graph has a cycle between k and 2k. If yes, I'm happy. If not, I contract an h and I repeat and repeat. At the end, I either will find a cycle or I will have a proof that there's no long cycle at all. So, but again, so this is you can say it's a color coding, but it's a color coding with one additional trick. And if you want to apply the same for directed idea for directed graphs, it's already problematic. You need to do more. And the problem is that for directed graphs, this argument that if I want to contract, if I contract an h, then I will still have a cycle of length at least k in the graph. It's not true, actually. Okay, and then but still, so color coding is a very powerful technique. So, and it's applied for many cases, and it's also not only work for graphs for paths. Of course, it works also for graphs of bounded trees. And but there are situations even about paths when color coding doesn't work. And the other quite powerful and also well-known technique is based on, it comes from graph minus. And in parameterized complexity, people call it, this technique usually win-win. And why it's called win-win? Because in your all type of arguments are either your graph has a small trivets, and then you win because you can do dynamic programming on graph of bounded trivets and solve your problem. Or if your graph doesn't have small trivets, your graph has a very nice structure, and then you can exploit the structure and solve the problem. So this is general framework. It goes from 1980s from Robertson and Seymour, who was applying. So basically, the algorithm of Robertson and Seymour on this joint path problem, it's basically using this strategy. Right? Of course, the implementation of the strategy could be quite complicated, but it's yes. So the algorithm of Hans Bodlander for longest path, it's again the same win-win approach. So what this algorithm was doing, so what Bodlander proved, that either you have you just perform depth first search in a graph, and either you find a long cycle, you win, right? And if you cannot find, either you find a long path, you're happy. And if you didn't find long path, you also compute trivets. You can show that the trivets of your graph is small. And this is yes, that's the. And of course, bidimensionality theory is also based on the same win-win approach. And there are a lot of works there. But the problem, or the devil, is in the details, right? So how to prove that your graph has a good structure? What is a good structure? So let me just give an example of what is a good structure is and how to use it. So this is based on our joint work with Ivona Bezakova, Radu Kurtik-Apyan, and Holger Dell. And the problem is the problem appears quite innocent, and actually it was one of the coffee breaks at Simon's Institute, and then Ivona asked us, come on, guys, you know everything about paths, which is not true, right? And then she said, why don't, so what do you think about the following problem? So the problem is called detour. And I have two vertices, S and T. And I can compute the distance between S and T easily, right? And then I'm asking if there is a path between S and T, which length is longer than the distance between S and T. And then, so when I parameterize it, I ask if there is a path between S and T, which length is at least D, distance from S to T, plus K. And here the parameter is K. And again, so just the sanity check, if we can do color coding here, I don't know, it doesn't look like, right? Because if we try to apply, if we try to color code the detour, the length of detour can be much larger than K. So, for example, yes, even and then so with this setting, color coding doesn't work. But then, so still it's possible to show that detour is FPT on undirected graph. And the idea of so just a very general idea, I want to use graph minus. So what I know about graph minus? I know that for every undirected graph, if I have a large trivets, then this graph should contain a large grid as a minor. Right? And consider just the most simplest situation. So I have a grid, and on this grid, I have 2 points S and T. So say I have a grid K times K grid. Then the distance between these points, whenever I put these points on a grid, is of order of K. But I can reroute in the grid and obtain a detour of order of K square, right? So when I have a grid, I can always use the structure of the grid to have a long detour. And this means that if the trivets of my graph is large, then I always have a solution. So this approach, it doesn't work exactly, or I hide a lot of things under carpet. So first of all, if my graph has a large trivets, I don't have a grid, but I have a grid as a minor. So it's not entirely grid. So rerouting here is much more complicated. But the worst thing is also that there's no linear bound between the size of the trivets and the size of the grid somehow. But what we obtain, so we show that the problem of computing an ST path of length at least distance st plus k is solvable in single exponential time in k. And the idea here, yes, it's again the win-win approach. So either we have a trivets of order of k, and then we can apply known technique to solve to find the longest path between the longest ST path, or there is detour. And the argument that there is a detour is that if the trivets is large, then we can exclude some structure. This is a structure. It's a tetrahedron, or it's a K graph, a complete graph on 4 vertices. But from this complete graph on 4 vertices, you also subdivide, or you replace every h in this graph by a very long path whose length is at least 5k. And then the main arguments in the paper are, well, first of all, you have to prove that when you exclude this, when the trivets is large, then this structure exists. And the second thing is also, which requires some work, so how to reroute in this structure to show that you can always use extra edges of this structure to obtain a long detour. But this is a technical detail, but this is possible. So why I'm speaking about these things? Because I'm really interested in this open question. So the question is detour, or what is the complexity of detour problem on directed graphs? So once again, what is the problem? I have a pair of vertices S and T in directed graph now, and then I ask if there is I am asking if there is a path from S to T of length at least distance from S to T plus k. And it's the problem FPT. So if there is an algorithm of running time f of k poly n, and actually it's even more embarrassing. I don't know even if there is a polynomial time algorithm which finds just a longer detour in polynomial time in a graph. And of course, I don't know if the problem is xp parameterized by k. So everything is possible here. And actually, with different people, we spent quite some time on this problem. And the first approach, which seems to be quite natural to try for this problem, is to imitate this win-win approach from undirected graph to imitate it for undirected graphs, to imitate it on directed graphs. So for directed graphs, now we have a quite powerful tool developed by Kenichi Kawarabayashi and Stefan Kreutzer. So they have a quite deep theorem saying that if you, which roughly is saying that if a graph has a large directed trivets, then it should contain a large grid, directed grid minor. Okay, I'm not saying what is a, well, this is on the picture, there is example of this grid minor, and I'm not saying what is a minor in directed graphs. It's just to get some feeling. But there are several problems with this approach. First of all, so when we look at directed trivets, it behaves algorithmically quite different than undirected trivets. And also we know that, for example, Hamiltonian cycle or Hamiltonian path can be founded in polynomial time on graphs of bounded trivets, but the dependence is XP dependent. So it's polynomial, but it's not fixed parameter tractable, parameterized by directed trivets. Okay, so this is the first thing. So even with this type of approach, it would be quite unlikely to obtain FPT algorithms, but still we don't know even about polynomial time algorithms. So maybe this could be used for polynomial time algorithms. But the second problem, which is even looks more difficult here, is that it's quite difficult to find to do rerouting in grid minus. And this is somehow, even if you have a large directed grid as a minor, it's not clear how to do rerouting, if possible at all. So basically, so far, this looks like a dead end to me. But again, until the problem is solved, it's I shouldn't say that. And this also just motivated us to try just a direct attack on the problem. Forget about grid minus. Let's just try to, again, come back to color coding, come back to dynamic programming, and try to do the work. But first of all, even to understand, so in order to have a direct attack on the problem, it's makes sense to understand how a much simpler question. So the much simpler question, I even don't want to find a detour between S and T. I just want to find a path of length at least K between vertices S and T. Right? And again, so of course I can use the huge hammer of a graph minus, right, to use grid theorem to find this, to claim that this path exists. But since if we don't believe that this type of arguments will be transferred to direct graph, so then what's the point to use them? And just if we try to use color coding, or well, color coding we cannot use again here directly, again because the length of this path can be very long, right? And again, color coding works only when we have the length path of order of K. And you remember when I started speaking about cycles, I was speaking about contraction trick. So definitely, I would be also interested if I can do contraction trick here. But here, once again, what is a contraction trick? So for cycle, the argument was if I have a very long cycle in a graph, if I can contract any h in the graph, then still in the new graph there will be a long cycle. Here, it's not entirely true, right? Because here, what can happen? So if I don't know where this path is. So if I just contract any h in my graph, it could happen that the endpoints of this h are very close to the endpoints of the path, to the vertices S and T. And then when I contract this h, I can destroy long path, and in the new graph, I will never have a path of length at least K. But then comes another trick or another idea. So basically what I want to do, I don't want to contract edges arbitrarily. So, but if I, for example, if I have a quite long path, and quite long path here is if I have a path of length at least 2K, then I can guess the prefix, the first K vertices. Well, I cannot guess the first K vertices of the path and the last K vertices of the graph. But if I just do a random coloring of a graph in two colors, then with quite good probability, I will have that the first K vertices, that the prefix of the path is colored in one color, and the suffix of the graph is colored with another color. And then actually it's quite good, right? Because this is a lot of information. Because now if I, the only thing which I was afraid that if I contract an H which has one endpoint close to S and the other endpoint close to T. But when I have a two coloring of the graph, I can say that, well, just if I contract an H which is a monochromatic, then I still will have a long path in the graph, and then this is exactly the idea of the algorithm. So the algorithm will be, again, I start from color coding and I check if I have a path between S and T of length between K and 2K. If there exists one, I'm happy, I stop here. If not, I'm using this two coloring, or it's called also random separation. So I use random separation, and then with this random separation, I contract an H, which is not monochromatic in a graph. And again, it guarantees that the resulting graph is either no instance or that I obtain equivalent instance of the problem. Okay, and so again, so I'm also trying to use to ask the same question: what's happening in directed graphs? And surprisingly, in directed graphs, this question becomes more complicated, and also just because in directed graphs we're not always allowed to contract an edge, because by contracting an edge, even if it's a good edge, we still can mess up a lot in the graph. And actually, surprisingly, this question was also, at least we didn't see it, and this is an IPL paper with Fahad, with Daniel, with Miraf, and with Saket. So basically, we try to use the same idea. Of course, for directed graphs, things becomes a bit more complicated, because instead of contraction and edge, you will have to use some structural properties. But at the end, again, so you can combine color coding, combine it with random separation, and then gain some structural results, and basically reduce the problem of to the problem of finding a shortest path in a graph, and then this is it. Okay, so at least we are able to solve a simpler variant of ST path problem without using any graph minus, and with color coding and with some additional ideas. And then actually we try to push it, and we push it and we push it, and finally this is a joint work, unpublished so far, joint work with Piotr Golovach, William Loche, Danil Sagunov, Kirill Simonov, and Saket Saurab. So basically, what we try to do, we try to again to extend this ideas of color coding and random separation, and of course, and we have to do it on the top of dynamic programming approach. And then basically we are trying, and at some moment we just got stuck, and we got stuck at exactly the case. So we will be able to proceed with dynamic programming and with these ideas if we will be able to solve a 3 disjoint path problem in polynomial time. So 3 disjoint path problem is the problem I have 3 pairs of vertices in a directed or undirected graph, and then I'm asking if there are vertex disjoint paths connecting the terminals. So these pairs. Yes, unfortunately, this problem isn't complete in general. But if on some graph classes we are able to solve this problem in polynomial time, then the Tour problem is also solvable in polynomial time. So, for example, by Robertson-Seymour, we know how to solve 3 disjoint paths and actually any k disjoint path in polynomial time on undirected graphs. So this also implies that the problem is solvable in FPT time in undirected graphs. And also by result of Schreiber, there is a polynomial time algorithm solving k disjoint path in directed planar graphs. And yes, and there is also FPT algorithm of Marek Tsigan and other people solving even in FPT the problem on planar directed graphs. But we don't care. We need only polynomial time algorithm. So Schreiber algorithm is also good for that. So this means that this problem is FPT on planar D graphs. And the interesting thing is that, well, at first glance, it looks like we can solve the problem without using the big hammer of graph minus on undirected graphs. But this is not true, because somehow to solve 3 disjoint path, so the only thing I know is on a directed graphs how to do it is to go through Robertson and Seymour, and this is again it's the core of graph minus. So still it looks like a graph minus here are unavoidable, but just out of curiosity, it will be interesting to just find out algorithm which for the tour on undirected graphs, which uses color coding and some tricks, of course, on top of that. So, okay, so just out of curiosity, so we have an algorithm which works in time, so which solves the detour or beyond the shortest path. It finds the path of length distance plus k. And you can ask, but why it's additive? Maybe we can also find a path of distance times k, right? Or maybe we can even look at the above guarantee with multiplicative bounds. Well, unfortunately, this is will not happen, right? This is just the problem is in P-complete for k equal to 2, and the reduction is pretty simple. So I just take ST, I take a path of length n between S and T, and then I also add a graph G connected to this path, and then for k equal to 2, so the question is if there is a path of length 2n from S to T, it just reduces to the question whether graph G has a Hamiltonian cycle, right, or Hamiltonian path. So this is an NP-complete problem. But somehow, surprisingly, at least to me, surprisingly, for parameter which is called girth in the graph is the length of the shortest cycle in the graph. Actually, it's possible to show the multiplicative above guarantee bound. And again, the tool here is the win-win approach, but we have to obtain a different structure, and then to show that for these different structures in graphs of large trivets, we have that many detour of this size. So the open questions about multiplicative bounds. The first question is that our algorithm, which computes a path of length girth of a graph times k, it runs in time, which is a quadratic exponential. So definitely the question is whether single exponential algorithm is important. It's just because when you have a single exponential time algorithm, this algorithm will definitely match the bounds, or at least asymptotically, of the best known algorithms for the longest path or longest cycle. And for directed graphs, I have no idea what's happening, and it's really interesting. It's this the same type of bounds definitely makes sense in directed graphs, but again, everything is possible here. And finally, I want to speak very briefly, so in the remaining 3 minutes, about extremal graph theory and why I really like this topic, because this is the area where the big hammers like color coding and the graph minus, they do not work. And so what is extremal graph theory? So when imagine we just start growing a graph from empty set, from empty graph by adding edges, right? So when the graph becomes sufficiently dense, it's become a Hamiltonian. So the typical question of extremal graph theory, so at what moment we can say that the graph is Hamiltonian, right? And the famous theorem here, it's actually it's one of the papers from where the whole graph theory started, is the theorem of Dirac from 1952. And this theorem says that any two connected graph with n vertices with minimum degree delta contains a cycle of length at least twice, minimum twice delta and n. And minimum here is just because if delta is sufficient, if more than n half, then the graph is Hamiltonian, right? So the cycle cannot have more than n vertices. And this is actually extremely important theorem in graph theory, because this is from where the extremal graph theory started, and there are a lot of work and papers which were improving, extending this type of results. But from an algorithmic perspective, it's very natural to ask this question. So if you look at the theorem, at the proof of the theorem Dirac, you can make it constructive in the sense that if I give you the graph, I can construct a cycle in this graph of length at least 2 delta. Can we construct a cycle which at least slightly larger, and a cycle of length twice delta plus 1? And surprisingly, so there's a huge extremal graph theory which was developed for Hamiltonicity. It doesn't answer this question, and it's very natural and understandable why it doesn't answer this question, because from the perspective of graph theory, so when we are looking for a cycle of length twice delta plus 1, we know for sure that there are graphs with this condition which do not contain there are graphs which do not contain such cycles That's the end of the story. So graph theory doesn't care about this type of graphs. End of the story. And if you look at all these amazing methods developed in graph algorithms for computing paths, again, as a color coding, all these type of techniques, they cannot be used to answer this question, just because this cycle can be very long, and its length can be much longer than k. So again, so this type of tools are also. And it looks like we need completely entirely new methods, or we have to so what's happening here? And again, so basically, actually, we were able to prove algorithmic result for this type of problems. So we give an algorithm which in time 2 to the k decides whether two connected graph contains a cycle of length at least 2 delta plus k or n. So this is like a parameterized version of the Dirac theorem. And actually, okay, I ran out of time, so I skip this part. So actually, we prove a more general result. So if you're interested, the paper is already on arXiv now. So it's so basically we solve even more general problem here. And the type of proof here is you definitely have, of course, you have to use color coding. You have to use other tricks from parameterized complexity. But what I find really fascinating for this type of problems, that you really have to go inside so the graph theory, and you really have to see how the classical extremal graph theory proofs how they work, and out of that. And you have to make them algorithmic, and then yeah. So there are a lot of things happening here, and basically, so the nice questions, which again, so it's I like it a lot, and this is a question again on algorithmic extremal graph theory. There is another very classical result of Erdos-Galai from 1959, which says, so like okay, so one statement is here, but the other statement could be that if every graph contains a cycle whose length is at least its average vertex degree, right? So here it's nothing. It's exactly the same statement here. And then what happening? So can we find a cycle in a graph whose length is at least average degree plus 1, or average degree plus k? And of course, this question is meaningful only when the graphs are too connected, because otherwise the problem is an NP-complete. It's easy to show this. So this is another open question, and yes, and could be quite exciting. So to conclude my talk, actually, yes, it's. I think this the citation from Albert Einstein is perfect here, but also it's also a perfect fit for any other set of nice and fundamental problems. So the more we learn about them, and we definitely will learn for the last 60, 70 years of work in graph theory and in algorithms, we learned a lot, and still we don't understand a lot of fundamental things about paths and cycles in a graph. And finally, I really want to thank all my co-authors and colleagues with whom I collaborated on this long path and long cycle projects. And thank you very much. Yes, I'm ready to take questions.
Okay, thank you, Fedor, for this very nice talk. So yeah, if anyone has any questions, please, yeah, you can raise your hand in the right-hand side. In the meantime, there was one question during the talk, actually, by Tore Husfeldt. The question was, what happens if I replace 3 disjoint paths with 2 disjoint paths in that statement? Which was...
So far, nothing, right? Because on directed graphs, it should be the same. If I remember correctly, I think 2 disjoint paths on directed graphs should be also NP-complete.
Okay, any other questions? So maybe I have a question. Oh, there's a, okay, Tore has an answer. but does it imply the other property?
In what sense?
Maybe, okay, I can try to get Tore here if he is willing to talk to us.
This is no, I cannot unmute Tor, but probably Andreas can.
Yeah, no, he should. See if this works.
Wow, I'm not sure this works. No, yes, Fedor, hi, nice talk. You had a result that said if a graph for a graph class, I think it was called C,
yep,
that allows 3 disjoint paths, you could establish the existence of. And this was some slides back. Right, and the question there was, is 3 disjoint paths necessary for that statement? Is it obviously false with 2 disjoint paths, or can you just not prove it?
No. Okay, now I got the question, and yes, it's a very nice question. I don't believe. I think that the 3 disjoint path is a more difficult problem. So definitely, if we know how, if for some class we can solve it, but it's not like if we're able to solve the detour, we can solve on this class 3 disjoint path problem. I don't know this, but I have no reason to believe that this should be correct.
Thank you.
Yeah, so that's all. Yeah, but definitely it will be really nice to see the equivalence of the problems, and then we will say, okay, this is a nice. Yeah, no, we don't know. Yes, Rolf's question: can you tell if a given ST path is a longest ST path? No, because basically it's just a Hamiltonian path problem, right? So imagine the vertices S and T are adjacent. And I ask if my graph is a Hamiltonian, then the longest path is a Hamiltonian path, right? So it's an incomplete problem. So it's... So the decision version of the detour problem, no, because for the decision version of the detour problem, I'm just asking you if I give you parameter k, right? And the distance I can compute, it's the shortest distance, right? And then I just asking if the given path is of length at least some number. This I can... Yeah, but maybe there is a path which is so. I think there's a confusion here, because one question is if this is the longest path, right? And here, so by the and here we just ask if there's a long path whose length is at least some bound. So one thing we can check in polynomial time, and the other thing is incomplete.
Right. Yeah, actually, I had a question also. So, I mean, you talked about a lot of techniques. So, what about weights? I mean, if I have edge weights, my parameter is going to still be the number of edges in the path, but I want to know if there is one of like certain length in terms of edge weights. I mean, which of the techniques works and which don't?
Well, there are a lot of techniques. So color coding should work for that, right?
Right, yeah.
Dynamic programming. And then there's so I think so so Bjork and Husfeldt Karski Klavista technique, it doesn't seem to work for the weighted things. It's like it's way too much. So when you start using representative sets, it's again works. When you use the techniques of Quartet and Williams, I don't think it works. So you really have to look at the technique.
Yeah.
And this is why there are so many of them.
Right. Okay. Interesting.
Yeah.
Okay. Any more questions? Last chance for a question. Doesn't seem so. Well, otherwise, thanks again for the nice talk. And yeah, I hope to see a lot of you in the discussion session, which is going to come next.